All right, two brief announcements, unless you want to add anything to this. The AED's next meeting is Thursday at 7 o'clock over in room SEC 100. If you're interested in showing up, you guys going to have free food?
Yes, I'm working on getting Subway this time instead of pizza.
All right. It's all right. So we got, and if that doesn't work out, I always highly recommend Freebirds.
Freebirds. Okay.
See, everyone's like, what? The original Freebirds in Santa Barbara? No. No. I've never been to the one in Santa Barbara. I've been to the one in College Station. But that was number 2. But never been to Santa Barbara's. All right. So 7 o'clock next Thursday, AED's third meeting. Lots of interesting things going on there. Also, we have another meeting, another announcement. This is AMWA. I don't know how new of an organization this is. Apparently, it's fairly new. They're having their meeting on the same day at 6 o'clock, and they're also having free food. So just look at it this way. You can start planning how you're going to eat for the rest of the week. If you start joining up all these different organizations, you can actually probably have a free meal every night, and it also buffs up your resume. Guys, I do not know if they do not allow you in. I suspect that they wouldn't, because they know what it's like to be discriminated against. So I don't know if this is a good way to meet girls, though. I'm just saying. Anyway, if you're interested in going to their meeting, they're going to be in the Corpus Christi room on the 4th at 6 p.m. So go there, then go to AED, and then you'll have a meal. Who can tell me what month this is? All right, what is October? A lot of you are thinking like that. Let's try again. What month does October usually, or is it usually casted as?
Gustatory receptor awareness.
That's right. It's female breast inspector, right? Now, I have a couple of these T-shirts. All right, I have a couple of these T-shirts, and ladies, I'm sure you're really going to want to wear one of these. Guys, in support of our women, we should wear these. Now, the problem is all the T-shirts I have 13 of them. I'm going to give away 2 today. I have 13 of them. And they're all mediums. Now, for those of you who like to wear really, really tight shirts, you can show off those pecs, show off. Yeah, I'm a little disappointed there is no such thing as a, prostate cancer month, but, we do what we do. All right. Anyway, so I'm going to throw out 2 questions here in a little bit, and if you answer it right, you get a T-shirt. Yeah, I know. Yeah, you're lucky I just don't have a T-shirt cannon. That would be a lot of fun. What we're going to do today is we're going to talk about the special senses. And the special senses are kind of fun because, well, they're special. They are different than the somatic senses. In other words, touch, pain, temperature, so on and so forth. And there's many reasons why they're distinguished, but the primary reason why they're distinguished is because each of these special senses have an organ dedicated to the reception of the stimulus that they're actually receiving. And what we're going to start with is we're going to start with the sense of smell. All right. Now, what we're looking at here is the inside of your nose, and we're looking at what we refer to as the olfactory mucosa, and that's just the cells that line the inside of your nose. All right, that's your nasal cavity. We have a bunch of different types of cells that are located there. We have supporting cells, and these are the cells that we hate because they secrete mucus, especially around this time of year. Everyone here got the sniffles? You know why? Because we all can't stand oak. That's why. All right, we have basal cells. Basal cells, their job is to actually give rise to the olfactory receptor cell. And the olfactory receptor cell is actually what we actually care about. All right? Now, this is actually nervous tissue. It's an afferent neuron that's been slightly modified. And what's not real clear in these pictures is, well, you can kind of look at it here. It's these grayish-blue looking cells in our cartoon. And they kind of look like onions. See that? I mean, they kind of descend down, and they have this kind of little bulb at the end, and then they have these little tiny cilia that kind of hang off. See? Like an onion. And this cell is a cell that actually detects smell. All right? It detects the chemicals. They're chemoreceptors. All right? And what they have is they are responsible for actually picking up what are called odorants. All right, now what is an odorant? Odorants, simply put, are the molecules that make up an odor. And we started talking about this briefly last week when we were talking about, didn't I use the example in here about the cherry limeade, and then everyone just kind of threw up their hands and said, I have no idea what you're talking about? Remember that? Well, if you think about a cherry limeade, and I use this example because it's simple. There has two different flavors to it, right? What are the two flavors? You remember? Cherry and lime, yeah. So, you can smell a cherry limeade and you go, cherry and lime, right? Real simple. All right. And so its job is to actually detect those two components, for example, in our cherry limeade. So one odorant would be cherry. The other odorant in this case would be lime, and together creates the cherry limeade smell. All right. Now, each of these individual cells are responsible for recognizing or responding to just one discrete component of an odor. All right. And what it does is once it fires, it sends its information on up through to what is called the olfactory bulb. And within the olfactory bulb, there are a series of cells in there. One of them, type of cell, is called mitral cell, and these are located in structures called glomeruli. And within the glomeruli, the signals that are being received are sorted, and the sense of smell is basically discriminated there. I'm feeling a little bit off because I'm still thinking about where I'm going to ask you guys questions so I can throw t-shirts out. I'm real excited about the t-shirts. All right. Now, in essence, what we're doing here is our brains are not responsible for actually getting all the information from the olfactory mucosa. In other words, the smells that you perceive are the result of the processing that's actually being done at the level of the olfactory bulb. And then ultimately that information is sent up to the olfactory centers of the brain, and then that information is then going to be associated and parsed, and then you're going to be told, oh yeah, this is what you're smelling. And I tried to use a really poor example last week when I was talking about, okay, and you got that little yahoo who's sitting there going cherry, lime, and actually hits grape and puts a little bit of grape in there. And you wouldn't be able to detect the grape, even though it's in there, because your brain is sitting there going, okay, I smell cherry, I smell lime, and there's kind of grape, but who cares, because that's not really important. And so I'm really going to focus on the two major ones. All right, and so your perception is cherry and lime. So that's kind of how smell works. But in order to understand it a little bit better, we need to think about what an odor is. And I'm going to use an example of an enophile. Who can tell me what an enophile is?
The person that likes wine.
There you go. We're going to start with that one. All right. Everyone knows what an enophile is now. It's a wine lover. All right. And have you ever seen anyone who drinks wine? How do they behave? Someone drunk. There we go. Woo-hoo. Kind of snooty, right? They're haughty. They sit there with their wine in their glass. They pour their wine. If you've ever gone to a wine tasting, you watch one of these people and you kind of roll your eyes. They dip that glass and they put it in their hands and they swirl it, right? Why are they swirling it? To aerate it, right? That's to waft it. I like that. That's good. Waft to aerate. In essence, what they're doing is they are releasing the volatiles. In other words, the thing that you want to smell, the things that you can smell, one of the characteristics is that those molecules within an odor have to be volatile. Now, when you hear volatile, don't think explosive. Think it's capable of being released from whatever it is. For example, right now, if you were to sniff your desks, could you smell anything? Please don't sniff your desks. You'll be very, very disappointed. Right? Could you smell anything? Is that plasticine surface, does it or is it volatile? No. Could there be things on it that are volatile? Yes. All right? So the things we'd smell is the last 20,000 people who sat there in front of you. Joy of joys. All right? So that's the first thing. It has to be easily vaporized. And that's what an enophile is doing. He's sitting there swirling his cup, or glass, over and over again to kind of mix it and allow those volatile components to actually rise up out of the liquid and get in the air. The second thing they do then is they, if you ever watched them, they stick their nose right in the glass. All right? And that's not because, well, they're impressive. Actually, what they've done is they've trapped the volatiles in the glass, and you're now sucking it into the nasal cavity so that it can waft over the olfactory mucosa. Now, barring anything else, nothing's going to happen unless those chemicals can somehow get to the olfactory cells, right? And the way that they're able to do that is they have to be able to penetrate through the mucus that is there to protect the nasal cavity. So the second characteristic of a odor is that it has to be water soluble, because mucus, for the most part, is 99% water plus 1% mucins, which are proteins, plus a couple of other things. All right? So it's mostly water, and so when you're smelling something, the reason you can smell it is because it actually penetrates and goes through that watery layer of the mucus. All right? Now, once that receptor is bound, that's going to activate the cell, and that's going to send that information forward to the olfactory bulb, and which is going to activate through the mitral cells, which are going to sort through all the information, say this is important, this is unimportant, blah, 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 blah. Let me tell you what's going on, brain. Send that information up to the brain, and the next thing you know, you perceive a smell. And that's what enophiles do. Have you ever watched them? I keep bringing this up. Have you ever watched an enophile? Hints of raspberry currant, some tar, a little bit of oak. Some harsh overtones, you know, and they have that little snooty look on their face. All right? But what are they doing really? All right? They're actually doing what we just described. They're not only releasing the majority volatiles, but they're also looking for and trying to isolate those minority volatiles, those minority odorants. And so every now and then you hear, you know, the hints of currant. What are they doing? They're basically going back to that odorant memory that they may have and say, you know, I've smelled black currant. You know what black currant is, right? Yeah. You know, go get yourself some black currant jelly. You won't be disappointed. Good stuff. You know, and they're like, this smells like that black currant jam that I had when I was 7 years old. And so when they say hints of currant, that might be what they're actually talking about. All right? They're actually picking up these minority flavors or minority odorants to actually bring them up. Now, when an odorant binds, it binds to the receptor, it activates the receptor, but you don't want to keep it bound. That doesn't make sense because you want to be able to remove that so that your next, or that receptor can be activated a second time. Right? You want a series of activations, and so in essence what's going to happen is that you want to remove any of the odorants as they bind up. And so this allows you to keep being stimulated as time passes. Now, olfactory signals in a very simple way actually travel two different routes. The first is through the limbic system. This allows you to coordinate smell and behavior. All right? Let's do a test here, even though we can't smell anything. If you smell hot, freshly baked chocolate chip cookies, see, I just saw the faces. I was just like, I mean, that's a behavior right there. It's like, ooh, chocolate. You know, right there. You walk into your house and you smell that, instantly, you're happy and perky. All right? All right, here's a fun one, guys. Guys, you know this one. Ladies, you may not. High school, gym. The locker room after gym class. No, yeah. I did play high school football. You can tell, right? I had a guy on the team. He never washed his undershirt, his underpad shirt. Every day before practice, he'd pull it out, stiff board, bang it, to loosen it up. How do you think that room smelled? Yeah, it was great. The second place that you're going to go is going to go through the thalamus. Here, you're not going to synapse. You're just passing through the thalamus. The thalamus. Sorry, I'm still thinking about the T-shirt. All right, you're going to go through the thalamus, go onto the cortex without actually synapsing, and here is where you're going to get that conscious perception. All right. In other words, you're going to be able to get that fine discrimination of smell, where you're like, yes, I do smell these fine things in the wine. Or when you're sitting there over a plate or a bowl of steaming soup, and you're sitting there going like this, and yes, I can smell the wonderful herbs that have been put in this, or the pepper that's been cooking. Or when you're walking across campus in the springtime and you start smelling that barbecue or the hamburgers cooking out on that open grill. I should not be teaching this late in the day. I get really hungry. All right, anyway, so that's basically smell. All right. I want to bring this up just because it kind of paints a complete picture. But inside the nose, there's a little structure called the vemeronasal organ. And in lower organisms, especially snakes, the vemeronasal organ is a very important organ. In humans, not quite so much, because its role is to play, or it's responsible for detecting pheromones. All right. Now, what pheromones are and what the vemeronasal is responsible for is actually governing reproductive and social behavior. In rats, pheromones play a major role in reproductive behavior. Humans, not so much, all right? Now, when we talk about pheromones, this is not something that you're aware of, all right? It's not like, what was that movie? It was Ocean's 13. You guys see that? And he puts the pheromone on, and what does that girl do? I mean, she's like, it's like the one he's supposed to seduce, and she's like, panting all over him. No. Rats? Yes. Humans? No. All right? Never as powerful as seen in animals. All right? A rat, if you put a female rat in a cage that was occupied by a male, she will immediately reset her estrous cycle, and she will go into lordosis, which is basically lifts her tail up and presents herself for sexual congress. All right? I guarantee you, if you are buying things like this, that's not what happens. What pheromones do is they might make the opposite sex more willing to actually talk to you, as opposed to slapping you when you come up and say, "Hey, how you doing?" All right. So, if you see stuff like this, or you're tempted to buy stuff like this, male or female, no, not as powerful. It just makes you more open to the idea of actually engaging in social behaviors, hopefully leading to reproductive. All right. Gustation or taste is located within the oral cavity. All right. And so here we're going to have chemoreceptors, much like we saw in the nasal cavity, but instead of just lining the walls of the oral cavity, instead they're actually localized in structures called taste buds. And what I hate about this picture, it actually doesn't demonstrate what a taste bud actually is. I mean, it's like, oh, look, here's a tongue. Those little bumps on your tongue are not taste buds, all right? They're called papillae, and they have multiple purposes other than taste. In fact, on the front portion, anterior portion of your tongue, you only have about 300 taste buds. Not very many. All right? And then on the sides of your mouth, you have more taste buds that are pretty much dead after you get out of childhood. All right? These are over here. And then if you grabbed your tongue and pulled it out, you'd see this kind of line. All right? And these are another group of papillae. We're not going through the names just to save your stress. All right? And it's there that's where the majority of your taste buds are actually located. All right? And you can actually see, those structures, those papillae, there's not very many of them. But if you take one of those papillae, which kind of looks like this, and you look along the sides, that right here is a taste bud. And you have many of these taste buds along that papillae that are lining that back little wall. Up here in the front, very few. All right. Now, if you look at this, what you're going to see is these cells right here are what are called the taste cells, and they're kind of jam-packed close together, stuck inside this structure called the taste bud. And then if you look, you can see right here is this opening within the taste bud. All right, that's actually opened up to the external or the luminal portion of the oral cavity. And it's here where these taste cells are exposed to the saliva containing the chemicals that have been dissolved within it. And it's here that we're able to actually recognize taste. So these chemicals are called tastants, and when they come into contact with the proper receptor, they actually activate the receptor and give you the sensation of the taste. All right. Now, the lifespan of a taste receptor cell is actually rather short. It's about 10 days, which we've all experienced this. We should know this. Have you ever burned your tongue on coffee or soup? Yeah, it's a lot of fun, isn't it? How long does it take before you get that taste back? About 10 days. I'm not talking that little burn. I'm talking like put it in there and you're like spitting coffee out and running around rubbing your tongue. You know, I did not realize it was so hot. Right? Yeah. So that's by then their taste cells are actually are basically replaced by that point. Yes, ma'am.
I read somewhere that every part of the consistency like different taste of sour
Mm-hmm.
why.
Yes. So previously, that's what the evidence was, and what they've done now, or from my understanding, is that as they've looked more and more into how taste works, it's actually not true. It's that each individual's taste bud contains multiple cells within it, and whichever number of cells are actually located in it are going to give you the general response. But here's the other thing: each taste cell can actually respond to every single solitary type of tasting. All right, but they respond to a majority type of tastings. So, for example, we have here listed 5 tastes. All right, these are the different modalities. All right, back when I was in high school or college, I can't remember which was so long ago, there were 4. Apparently now there are 5. I feel old. All right, so we have the salty, the sour, the sweet, the bitter. Those were everyone knew that. And then we have this other one, which I pronounce incorrectly, I might add, umami. It's easy to remember that way, right? You're never going to forget that. It's umami. Someone's going to come up here. How do you pronounce that properly? Umami, that's right. It's Japanese and it means savory. All right. Actually, it means literally flavor or savory flavor taste, something like that. All right. Anyway, what each of these tastants do is they activate a specific type of receptor. So salty receptors actually open up a chemically gated channel, or it's believed that they open up a chemically gated channel and allow for the entry of sodium in. This is true for many minerals as well. So things that taste salty are allowing sodium to rush in, cause a depolarization in the cell, which ultimately activates an action potential in the afferent neuron going to the gustatory center of the brain. Sour is basically going to be caused by free protons. Where do we see free protons? Acids. That's exactly right. Everyone always thinks of an acid like hydrochloric acid. You see HCl, so it must be an acid. No, remember, when that acid dissociates in water, you end up with free protons. That is what gives acids its characteristic. It's the number of free protons that are available. So the availability of free protons actually blocks specific channels that give us a sense of sour. Let's think of some sour foods. Lemons. What do you think lemons have? Citric acid. How about Sour Patch Kids? Atomic warheads. I mean, look, we're talking food here. Come on. What do they have? That's a very, very confusing question. A lot of people don't know. What does it have? Oh, you don't know? What do you think? What do you think they have that makes them sour? No. Which type? I don't think so. They might. Acetic acid. Yeah, everyone's going to go out and go buy atomic warheads. But yeah, so what you're talking about here is basically acids that give you that sour sense. Right? All right. So that's working through another channel. Sweet binds to a specific configuration of glucose. All we got to do is mimic that shape of glucose and we get a sense of sweet. Think of all the sweeteners we have that are available to us. Sucralose, sucrase, or not sucrase. I mean sucrose, which is a disaccharide including glucose. I mean aspartame. Aspartame. You guys know what aspartame is? It's in Diet Coke. Oh yeah, it's fine. Can't take away my aspartame. It's actually a peptide. But it actually has a shape very similar to glucose. Yeah, it has phenylalanine in it. Right. So basically anything that can bind to the specific G protein coupled receptor will actually ultimately activate a second messenger system. All right, which will then result in activation or release of a chemical or neurotransmitter to activate things. Bitter is the weird one. All right. Many different things can actually bind to the sweets. Many different types of, it's the hydrogen. Many types of things can stimulate these salty receptors. But the bitter ones are very, very specific. And again, they are through G protein coupled receptors. There's about 50, anywhere between 50 and 100 different types of tastant receptors that recognize these different types of bitter tastants. And the purpose of the bitter tastant is to protect you. All right. Most things that are bitter are bad for you. You know, rotting food, pretty bitter. Alkaloids. Alkaloids are the chemicals produced by most plants to protect them from being eaten. Have you ever noticed that? Celery, bitter. Lettuce, bitter. Most vegetables, bitter. All of the medications are bitter. That's right. You know, that's why we put a spoonful of sugar. That's right. Help the medicine go down. That's right. And in essence, what we're doing here is eat chocolate. Chocolate's bitter. Yeah. Oh, come on. Chocolate's awful. I mean, you've all done it. You probably don't remember. You probably blocked it out of your memory. You were about 5, 6 years old. You walked in your mom's pantry. You looked up there. You saw chocolate. Of course, all you saw was the word chocolate, and you saw the pieces, but you didn't see it was baker's chocolate. And you got in there, and you had that big block of chocolate. You snuck into the bathroom. They're like, chocolate. And all of a sudden, it was just like, what have I just put in my mouth? This isn't chocolate. This is a trap. How does chocolate taste good? Why does chocolate taste good? Sugar, that's right. We get sugar. Bitter in very low quantities is not bad. Bitter in high quantities is a danger signal that says, get this out of your mouth, you're going to die. And that's what your body does. Basically, your response to bitter is usually, right? And this is innate. Children are born with this. Give a child a pea and watch what expression they give you. You know what I'm talking about, pea, a little, give them a pea, they're like, okay, I'll open my mouth again. Please don't give me that. Mm-hmm. Mm-hmm. Well, no. Why do we eat greens? Do we eat them for the vitamins? For the fiber. Where can we get fiber? All right. Here you are. You're a monkey in a tree. All right. You're a monkey in a tree. Yes, you're wearing clothes. Yes, you can talk, but you're a monkey in the tree. All right. What if you have a choice of eating in the tree? You have fruit and you have leaves. What are you going to eat? Right. Why? Sweet, has energy, lots of good things. And what do? You take the whole thing and you shove it in your mouth. You don't carefully peel that thing like we do nowadays. You basically take all that pulp and the seed, spit out the seed, and you shove that stuff in your mouth. There's your fiber. Then we learned that we needed fiber to properly process food better. So that's when someone evil came up with the concept of eating vegetables. Yeah, thank God for butter. Let's fry it all up. Yes, sir.
You talked about these being able to be replaced every 10 days.
Mm-hmm.
So would these be considered, neurons proper that are actually...
No, and in fact, these cells themselves, so this is the neuron, this is actually non-neural. These are actually epithelial in nature. That's a good question. I'm not going to ask you that, but yeah. Mm-hmm. Right, so you can think about it like this. Remember, our little cartoon here shows a single cell, but you can imagine as one cell is destroyed, it's pushed off to the side, another cell just kind of goes into its place. That's a good question. I don't know the answer to that. I'll have to look that up. My understanding is that there's multiple neurons that are associated with a particular taste bud, but whether or not each individual cell gets its own neuron, I don't know. That's a really good question. Fair enough. All right, the last one is umami. Umami. Right. This is actually triggered by a specific amino acid in humans and pretty much every amino acid in rodents. And this amino acid is glutamate. Why do we put it in there? Remember what we said umami means? Savory. That's right. And when you put MSG on food, what do you experience? Savory. It can rescue a really, really bland meal. All right? That's why it's put on everything. All right? So MSG is actually, or sorry, not MSG, umami actually activates through a G protein coupled receptor. And it gives the sense of savory. And this makes sense. I mean, think about, without even thinking about monosodium glutamate, think about a ribeye. You guys like ribeyes? I mean, I know I'm not talking to the vegetarians here. Imagine tofu. I'm kidding. Tofu is not savory. All right? Imagine a ribeye. When you're sitting there taking a bite of that hot piece of meat, and you cut through it nice and tender, and you put it in your mouth, right on that tongue, you start chewing, what does your mouth start doing? All right, now you're thinking about it. I can feel that piece of salivating. It's savory. You just fantastic piece of meat. And then you. No, I'm just gonna. My job is to torture you. Haven't you figured it out? Yep, that's right. So you get the sense, umami. It actually also recognizes nucleotides as well. And you can imagine, so the umami receptor is pretty much responsible for activating when we are consuming heavy protein meals, specifically cells that have nucleotides within them, meat, beans, so on and so forth. Now, your taste is not just what you have on your tongue and through these receptors. If it did, it'd be very, very sad. Really, a lot of taste is actually influenced through other receptors, especially your olfactory receptors. And you can test this out. I mean, go get sick. Please don't go get sick. But go and eat a bowl of soup when you're sick and tell me if you enjoy it. And I'm not talking about I feel sick, I don't like this. No, I'm talking about, can you smell the soup? No. Can you taste the soup? No. You can just feel something hot in your mouth and you're kind of like, okay, I've got to eat this. It's supposed to be good for me. All right? It's the olfactory receptors that actually make it interesting. And that's the same thing with the wine. You drink the wine. If you pinch your nose and drink the wine doesn't taste any good. It just tastes like grape juice. Not real exciting. It's when you have both components, both the olfaction and the gustation working together that gives you a sense of taste.
A friend of mine once in the gym lab smelled almost pure hydrochloric acid directly and was pretty much tasteless for a couple of months. What happened?
Well, tasteless. Well, probably because you burned a whole bunch of olfactory cells. I mean, that would be my first thought. But the other thing is that when you're inhaling volatiles, you're not just going there. They're actually circulating through, and so they actually may have overactivated and actually caused a little bit of destruction of the olfactory receptors, or sorry, the taste receptors as well. I'm guessing, As far as I know, it could be little tiny gnomes in the nose. All right. Should I give you a second challenge question? There is possibly a sixth tastant. What do you think it could be? Now, before you answer this question, let me point out something here. Our 5 different tastants can actually be categorized into things that our body needs and something our body does not want to have. For example, salty and sour are responsible for homeostatic balance of both salts, right, and minerals, as well as maintaining acid-base balance. You can kind of see that there, right? Sweets give us a sense of sugars. Umami gives us a sense of proteins. If you think you know the answer, put up your hand. Yes, sir. Yes, ma'am. That's right. Patty. There you go. This close. Guess what? I'll be passing more out over the next coming days, so you'll have lots of times to. Like I said, there's going to be 13 more of these. Yeah, fatty is a possible 6th tastant. And actually, there's evidence now that there are receptors throughout the oral cavity that actually detects free fatty acids. It doesn't work on triglycerides. After you break down the triglyceride and turn it into a free fatty acid, it actually activates a specific receptor. Have you ever noticed that fatty foods taste really good? Yeah. There you go. Now I'm not going to ask you that on the test. That's just more of a fun question. Yeah.
So, in the same line of thinking, do we ever taste like DNA, RNA, nucleic acid?
There you go. Yeah. Actually, and so, time out. Umami actually detects not only glutamate, but the 5' ribonucleic or ribonucleotide monophosphates, GMP and IMP. So, in essence, there's your nucleic acids. So, yeah. Yes, ma'am. Spicy? In the best category. No, spicy is actually detected by thermal receptors. So capsaicin actually binds to a specific thermal receptor on the tongue, and that's why you get a sense of heat as opposed to a sense of flavor. Now, that doesn't mean that it doesn't bind to receptors like, say, salty, and actually gives you a sense of saltiness to it, or maybe to sweet. But you're talking about multiple tastant molecules, but like a molecule like capsaicin binds specifically to a heat receptor or a thermal receptor, excuse me. Yeah. Yes. Yes. And so you can imagine you have touch receptors on your tongue. I mean, you can feel that, right? Yeah, people are going to start doing this now. Hey, yeah. Actually, the papillae actually serve multiple purposes. I mean, there's actually multiple somatic receptors in place there to ensure that you're not doing damage to yourself. I mean, for example, if you put, a piece of glass in your mouth, you'd probably want to spit it out, and your body would recognize, ooh, pain, spit out, right? Or let's be more realistic, Doritos, right? I mean, start chewing on a Dorito wrong, it gets, it's there to protect you. So you have thermal receptors, you have pain receptors, you have touch receptors, you have all these different types of receptors in your mouth to help protect your body from the damage that you can actually cause to yourself. I would say, well, the papillae themselves are actually just the structures. So, if you take your finger and you run it up and down your tongue, you'll notice that it's rough, right? And so the papillae themselves actually serves several purposes. We're going to get to that more when we talk about digestion. But in essence, what it does is it gives you a rough surface that you can actually hold on to liquids, actually be able to manipulate materials in your mouth. And it just so happens that specific papillae actually have these taste buds. And so you can imagine that many of these papillae are going to have multiple types of neurons that are actually going to be innervating into the epithelium that creates those structures, just to serve the purposes of touch and pain and so on and so forth. It's a big fat muscle too, so you have to be able to move it. Otherwise, we wouldn't be able to make these noises that I'm making. All right, well, those are the two easy ones. Oh, wait, yeah. So, just to point out again, signals go from the taste receptors, go to the thalamus, onto the brainstem, to the gustatory complex. And here, once again, we're going to take information that goes through the thalamus, send it to the hypothalamus, and we're going to send it to the limbic system. Love the limbic system. Limbic system rocks because it makes everything good. Or bad, depending on how you remember stuff, right? So, when we taste something, like anyone here, is a grilled cheese sandwich like comfort food? Yeah? Yeah, when I said grilled cheese, what do you think about? When you're like 7 years old and you're sick and it's cold and your mom makes you tomato soup and a grilled cheese sandwich. And maybe not tomato soup, but maybe chicken noodle soup. Right? See, all right, to those of you who are Middle East, it's a little bit of some grape leaves, your shawarma. My great grandmother used to make me kibbe. Best kibbe you've ever had, too. People are looking at me like, huh? And people from the Middle East, oh yeah. Good kibbe. That's so wrong. Yeah. That would be the unpleasantness. All right? And then ultimately, it's going to allow us to create those behavioral aspects that we normally associate with both taste and smell. So if you smell something really, really awful, like cooking Brussels sprouts or cooking cabbage, that is like the worst smell on the planet. Cooked? Oh my goodness. Mm-hmm. Mm-hmm. You haven't convinced me yet. Yeah, there you go. All right, now we're talking. See, this is how I get fed. Yeah, I don't like any food. Prove it to me. See? Yeah. Actually, they have more. Yeah. Yes. Well, I mean, we have an underdeveloped sense of smell, and we have fewer taste receptors than most mammals do. Yeah, I know. And just think about our palates, how much stuff we enjoy. You know, but also cats can't tell the difference between aspartame being sweet versus savory. They figure it's a peptide. So, because they're cats.
Yeah, or like goats eat metal cans.
They're not eating the metal can. They're just trying to get to the nutrients that are there. On the, yeah. No, it's just it's probably just a function of, you know, they have iron stomachs, I guess. I don't know. I don't know why they eat such awful stuff. You know, maybe their brains just don't have the same ordering of, you know, like what really tastes good and what doesn't. You know, I mean, I've watched my kids put stuff in their mouth that just defies understanding. When I see my child pick up my son's shoes and shove them in their mouth, really? We're probably just going to get through the ear today. I can already tell I'm having too much fun. All right. What we're going to do is we're going to talk about the ear now. And the ear is actually a little bit more complex because it actually is responsible for two of your special senses, hearing and balance or equilibrium. And if you look at the ear, it actually has three parts to it. And I know this is an anatomy class, but I just want to outline these to you so you understand how sound gets to the parts that actually allow you to hear things. So we have what we refer to as the external ear, which is responsible for transmitting sound waves to the inner ear, and it does so through the tympanic membrane that then passes through the ossicles and ultimately arrives here at the inner ear. So you can see the three boundaries. Here's the external ear, bounded by the tympanic membrane, the middle ear, which is bounded by the oval window. All right. Now the inner ear itself is actually fluid filled. All right, so it's completely filled with fluid, and it actually has two different sensory apparatuses associated with the inner ear. We have the cochlea and we have the vestibular apparatus. The cochlea is this structure right here. And if you look at this, let me erase all my garbage on this. What does it look like? It does. It looks like a snail. You can see there's its two little eye stalks, things that we beat with the sticks. And there's your snail. Right? I mean, there's the yeah, and that's why it's called the cochlea. Cochlea is Greek, I think. Is it Greek? Might be Latin, I don't know. Never took any of those classic languages, but it's snail. That's what cochlea means. It's snail. All right. The vestibular apparatus deals with the cochlea is responsible for sound. The vestibular apparatus, on the other hand, is responsible for your equilibrium. Now, just to give you an idea of where we're going and what we're talking about, hearing is the neural perception of sound energy. All right. Remember, sound energy does exist. Yes, ma'am. Eardrum, timpani, drum. So, perfect. All right. If I were to take anything, we'll start over here with a big giant trash can. All right. You remember a long time ago you guys took physics because everyone has to take physics, right? If I lift this off the ground, I've converted this and I've created what type of energy? And if I let it go? All right, but is the potential and kinetic energy equal to each other? Law of thermodynamics states it's conserved. But where does it all go? Sound and heat. Very good. Okay. So I dropped this on the ground. You heard me drop it on the ground. It was much, much louder than that. All right. So some of the energy that was imparted as it fell was transmitted as sound. So energy of sound does exist. It's not a made-up thing. All right? Now, what we're doing here is basically a sound wave is really just the movement of molecules colliding into other molecules. And so what you have is basically a rarefaction and a refraction of air particles bouncing against one another, creating a specific frequency as it travels through, or through space, or through the air. All right? Now, the further you are away from the sound, the more energy is lost. I mean, it's lost to the universe, right? I mean, into stuff that we can't use. So, for example, the people in the back, you can hear me just fine right now, right? See, these guys can hear me. You guys can't because the sound can only travel so far. It only has enough energy to keep pressing those molecules as they go along. Now, sound is characterized by three different things: pitch, intensity, and timbre. Pitch, simply put, is the frequency. So, you know, back in the days you learned about high notes and low notes. That's the frequency of the wavelength. So if you look at the length of the wave, or the distance between wavelengths, that will give you a sense of the tone, or the pitch. The intensity is loudness. That's the easy way to think of it. And that's going to be dependent upon the amplitude. So these two things right here are the same length, but right here the amplitude is different. So a loud note has a higher amplitude, a softer note has a lower amplitude. The last is the weird one, is the timbre. All right, and this is quality. Really what it boils down to is that a pure note is something that's real easy to identify, and what we do is then we put notes on top of notes on top of notes that give each sound its unique sound. It's a terrible way to define it. But if I say hello and you say hello, our hellos sound differently, right? Because we put different overtones as a result of our vocal cords creating these different overtones to make each of our voices sound unique. That makes sense? So even though we may use the same notes, we sound unique because of the different overtones that are put on that primary pitch. So this is what they're trying to show you here. There's one, there's the other. This frequency is the same, and then this one has a high frequency on top of it, which gives a unique sound versus the one that has the lower one. Now, with regard to the external ear, we have a couple structures that help guide the sound to the tympanic membrane. We have the pinna. The pinna is basically the skin and the flap of cartilage that we all know and love as the ear. Okay, that is the pinna. All right. Its job and its unique shape is actually designed specifically to drive sound and direct it to the ear canal. Inside the ear canal, which is this structure right here, is where you're going to see a whole bunch of little fine hairs and the ceruminous glands, which I can never pronounce properly, whatever. They produce basically your earwax. All right. And their purpose in all of this is actually to catch nasty things that can actually gather in your canal, and then they've slowly pushed outward with that earwax, or when you gather it up with a Q-tip. Then we have the tympanic membrane. And this is just a membrane that separates both the external ear and the middle ear. All right? When the sound waves travel through, that tympanic membrane begins to vibrate at the same frequency as the sound waves that are hitting it. Now, if you've ever listened to a drum or heard a drum, the way that a drum works is that it has to have equalized pressure on either side of the membrane. All right? So in other words, you could have a big drum like this. I can't draw to save my life, so we won't do that. All right? Think about a drum, all right? You got a drum, you're bouncing on, bump, 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 bump. What if you put your hand on the other side of the membrane? Does it sound the same? No. All right. And that's in essence what's going on here, is that we need to have an environment that allows that membrane to vibrate freely. All right? And so what we have is we have the eustachian tube that opens up into our oral cavity, actually back in the pharynx. You ever popped your ears before? You can do it right now. Or you can do it this way. All right? And what are you doing? You're basically opening up and you're equalizing the pressure on either side. When you go up in an airplane, you've had to do this before, right? Because as you're going along, all of a sudden you can't hear anything. You feel the pressure building up. So off you go and pop it, and now you hear things just fine. You're equalizing the pressure. And so making sure that the pressure is equal on either side ensures that the membrane vibrates at the proper frequencies when sound hits it. That's right, and it's eustachian tube, and it opens up into the back of the pharynx. Inside the middle ear, you're going to see three bones. These bones are responsible for taking the vibrations of this tympanic membrane and moving them over here to the oval window. But they don't just transfer vibrations. Their job is to actually not only transfer, but to also amplify. So here's your amplifier. All right, so there's three bones. It's the malleus, the incus, and the stapes, which is basically the mallet, the hammer, and the stirrup. I think if I ask you anything, it's like which one of these is not one of the three bones. So I don't know if I actually even asked that. But their job, remember, is to amplify. All right. So as the vibrations occur here, they're going to cause the same vibrations over here at the oval window. But the vibrations, even though they're at the same frequency, now because you've amplified it, you made it a much, much stronger vibration. And there's a reason for this. Have you ever been in a swimming pool and tried to talk to your best friend underwater? Yeah. Or if you're like that cute couple, you know, you're talking to the guy, you know, your significant other. I love you. I love you. I love you. I love you. And you're making kissy faces and you make everybody upset and unhappy about you. All right. But what do you have to do when you talk underwater? Can you just do it normally? No, you have to blah, 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 blah. Right? You have to be loud. You have to make your voice heard because you're trying to move water molecules, which are far closer together than air molecules. Right? So you have to do more work to get the same vibrations to travel any sort of distance away. And so that's kind of the same thing, is because remember, the inner ear is full of fluid, and so if you want that vibration to be penetrating through the canals of the cochlea, which we'll get to in a moment, you have to really create a lot of force to get that fluid to move. It's not as easy as the air. So that's why it's an amplifier. Now, when you hear loud sounds, there are muscles that surround those bones. And their job is to contract and to protect. Yeah. The malleus, the incus, and the stapes. They're actually malleus, incus, stapes. And their names in English, mallet or hammer, the anvil, so you got the hammer and the anvil, and then following that is the stirrup. And if you look at it, there's your stirrup. It looks like a stirrup, right? I don't know why they call this one the hammer. I guess it looks like a hammer, right? Not in any cartoon I've ever seen. No, they're connected. Yeah, it's basically three things that are connected together that are doing this. Absolutely. Yeah, so there's muscle that's surrounding it. All right. So the muscle sits there and acts as a brake to their gas. All right. And this is what I was trying to get at. So have you ever been to a concert where you were foolish enough to get right in front of the amp stack? Isn't that awesome? You know, you're like, all right, I'm in front of the amp stack. I'm going to get the full thing. And they come out and they say, hello, Houston. And then, whong! And after your eyes pop out of your head, you know, you're sitting there. And then after a while, it's not so bad, right? I mean, the music might be blaring at you, but you're like, yeah, this isn't too bad. It's because those muscles contract, and then they're no longer allowing the bones to move with the same sort of vigorous movement that they would in a normal environment. Yeah. Are the bones connected to the skeleton? No, they're actually localized within that canal, so they're not actually part of the skeletal structure. They're actually, I don't want to say they're free floating because that would be wrong, but they're not actually part of the skeleton itself. Right? It's not like the patella. Even though the patella is free floating, it's actually considered part of the skeleton. Yeah. All right. The problem is that you notice that it actually takes a little bit of time, and it's because these muscles are slow to respond. And when I say slow to respond, it takes about 40 milliseconds. So when you first hear a loud sound, what do? Right? And then after a while, it's like, oh, this isn't too bad, because by then the muscles have contracted and are now protecting your inner ear. Now we're going to start with the inner ear here. This is the hearing portion. What we've done with our inner ear is we actually unwound it. Remember what we said when we looked at the picture? What did it look like? Yeah, does this look like a snail to you? Looks more like a scorpion. See, all you got to do is just put a little there at the end. You got a scorpion. Okay, anyway. I guess that wasn't as funny as I thought it was. I'll throw some sneakers out there. All right. What we have here is, what we've done is we've unwound this just so that we can visualize what's actually going on, because it's kind of hard to follow the movement of fluid in a coil. So we're trying to unwind it just so that we can look at it easier. No, it doesn't actually unwind in real life. It's a nice, solid structure that's coiled, and then what you notice is that we have a canal that basically goes one direction and then turns around and comes back and goes the other direction. All right, and so that's represented in the coil itself. I'm going to back up here so you can see our coil. Come on. All right, there we are. There we go. There we go. Erased all the ink. So you can imagine what's going on here is that the canal what have I done? All right, erase all the ink on the slide. There we go. The canal goes like this, comes back around, and goes like this. Yes, it has to. All right. So that's in essence what it's doing. All right. So it's going all the way and then coming all the way back. Yes, it's up. Yeah, it's in its own little separate area. Okay. Now it's still connected. You can see here in our little cartoon. Look at that. So it's comes off, but it's still part of it. All right. Anyway, so what you'll notice here is that if you took a slice through it, this is a slice through it. What you're looking at here are basically the canal as it comes up and it comes back. And so what we have here is what is called the vestibular duct. That's the one that's leaving, going in this direction. It comes up and then it comes around through the helicotrema and then comes back around. Again, you don't need to know that. And then comes back around and forms what is called the tympanic duct, which is this lower one. So you have one canal up here and another canal down here, and in between you have a third canal. And this third canal is called the cochlear duct. Well, since it's named after the structure, it must be important. Okay? Now, if you have three ducts on top of themselves, 1, 2, 3, like that, then what you can say here is we've got a membrane between these two and a membrane between those two. This membrane is called the vestibular membrane. This membrane down here is called the, I want to make sure I'm saying it right, is the tympanic membrane. Nope, basilar membrane. Sorry. So basilar membrane. This is the vestibular membrane. And what we have is a structure inside this internal one, this central canal, this cochlear duct, that's called the organ of Corti. Now, the organ of Corti is actually the structure that is responsible for hearing. All right. If you were to look at the organ of Corti, which is really hard in this little tiny picture, I think there's a better picture on the next slide. Yes, we'll get to that in just a moment. Is that you're going to notice that it has one row of inner hair cells, not hair cells, but cells that have these little structures on top that look like hair. It has another group of hair cells, 3 rows of these. These are called the outer hair cells. And on top of these hair cells are these little tiny stereocilia that stick up, and it's these things that we're going to be manipulating to create action potentials. What we have here is a mechanoreceptor. So, how does this all work? Now, a sound wave has, we said, a frequency. It travels, right, a certain distance. And so what happens is when that oval window begins to vibrate, it creates a frequency wave that actually travels through that vestibular duct, up around the helicotrema, which is that point, and then back around to the round window. And it's carrying with it a certain amount of energy. All right? Picture a wave in a bathtub or a swimming pool. You do a cannonball, you see a wave, it's going to start moving away from the point of origin. And it's going to carry with it a certain frequency. And you can watch that frequency as it travels along the length of the pool. And that's in essence what's going to happen here, except this structure is really, really small. And so when you're thinking about waves, it's basically going like this. Comes in, and it's going to come down, and it's going to come into contact with that vestibular apparatus. Or it's going to come in, and it's going to come in contact with the vestibular apparatus. Or it's going to come in and come into contact with the vestibular, or I shouldn't say vestibular, vestibular membrane. All right? Depending upon its frequency. High notes, low notes, frequency. All right? Now, when it comes into contact, when you create pressure, a pressure wave, it's going to cause the membrane to do what? Go down, right? If I have a wave that comes along and pushes on my membrane, that's going to push down on the vestibular membrane. Now, in that cochlear duct, the middle duct, there's fluid. If I push on the vestibular membrane, what's going to happen to the fluid in here? It's going to press down and it's going to push on the basilar membrane, right? And then that pressure then is going to be transmitted back, and then it's basically going to be distributed away from that site. So the energy is basically moving in a circle. All right? Yeah.
So that means that the wave might not always go all the way down around the helical.
Right. Some will. Some really, really, really low come down here. Some that are even lower than that. I can't get that though. Imagine I'm a big blue whale. We come around and then come out here, and over on this end we have what is called a round window, and the purpose of the round window is to dissipate the energy in the wave. All right? Think about it like this. Have you ever squeezed on a long balloon? Notice we haven't even gotten a sound yet. Have you ever squeezed on a balloon? What happens at the end of the balloon? Right? That's all we're doing. You've dissipated the energy or the force that you've created by squeezing on the end. All right? Because it's elastic, and that's what happens. The energy gets dissipated. But you need that energy to actually activate your cochlea, right? Your organ of Corti found within the cochlear duct. Now, here we have the vestibular membrane. Here we have the basilar membrane, and we're saying it's moving up and down depending upon where that sound wave comes into contact with the vestibular membrane, like so. All right? Inside the organ of Corti, we have a structure called the tympanic membrane. The tympanic membrane is a stiff membrane, nice and hard. Coming up from the basilar membrane is where our organ of Corti is. We have those hair cells, and that tectoral membrane sits lying right on top of those hair cells.